Well, good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. Our webinar today is titled Smart Model Transfer, or SMT, Automation. In recent years, the field of structural engineering has witnessed significant advancements driven by automation and digital technologies. One such innovation is automated smart model transfer, which streamlines the process of transferring structural models across different software platforms. By eliminating manual steps, reducing errors, and enhancing collaboration, SMT empowers engineers to focus on design and analysis rather than using manual data migration. Today, we're going to join Fluor subject matter expert, Lorne Jensen, Fluor Fellow Eric Wey, and his protégé, Jonathan Litoff, to explore the benefits of using SMT. So Bradley, I'll pass it over to you for the HSE topic.
Thank you, Dave, and good day, everyone. For our safety topic, I will present an example highlighting the critical importance of communication, especially when changes are involved during design and fabrication. The safety topic today is based on an event that is considered the most catastrophic failure of a structural connection in the United States. It occurred in Kansas City, Missouri in 1981 at a recently opened Hyatt Regency Hotel. During an event, 2 walkways collapsed, resulting in 114 deaths, 216 non-fatal injuries, and trauma for the entire community. How could this have happened, and what could have prevented it? First, there were gaps in the communication of the design as a result of changes in engineering personnel and incomplete data transfer between detailers and connection designers. Second, and most direct to the failure, a design change was requested and approved outside of the formal review process. The connection shown in the bottom middle of the slide was changed from a single rod to a double offset rod design, without a complete review by the structural engineer. This resulted in the actual load bearing on the connection element to double in magnitude. The failure mode can be seen in the bottom right. What could have prevented this catastrophe? Of the many lessons learned and recommendations found in the post-event investigation, I would like to highlight the following. All design changes should be handled with a process that compels the participants to focus on potential issues. Circumventing the process has the potential for negative consequences, unforeseen by the requester of the change. And the review of detailer shop drawings should be performed by the engineer of record or a representative with direct knowledge of the project. This critical step ensures that the design was properly communicated and implemented by the detailer. I will now hand over to Eric for the feature presentation. Thank you.
Thank you, Bradley. This is the agenda that we'll be following for our presentation. Although SMT can be used for transferring data for many different fabricated materials, our presentation will focus on structural steel. The topics are set up in the order in which SMT is executed on a project. We will start with engineering and finish with shop drawings ready for fabrication. Along the way, we'll be discussing the innovative advances in SMT workflow. We have come a long way from the days of drafting boards and paper drawings. In the past, the only way a client could visualize the final product of their facility during the engineering phase was by using a 3-dimensional plastic model, as shown in the photo. These plastic models have been replaced with 3-dimensional computer models. With widespread use of computer-aided design, drafting boards have become a thing of the past, but the manual transfer of data from an engineering company to a fabricator is still common. A work process that is still used today involves an engineering company producing 2-dimensional CAD drawings, which include plans, elevations, and details. These drawings are released to a fabricator who produces erection drawings, piece mark drawings, and gather drawings. which are submitted back to the engineering company for review. This cycle is a manual process with the fabricator recreating the information transferred by the original two-dimensional engineering drawings in the fabricator's software and producing two-dimensional shop drawings for review. Much like the plastic models of the past, three-dimensional engineering computer models serve the purpose of showing how equipment, piping, conduit, and tray, instruments, and structural steel all fit together without clashes. It also shows the clients the space that they have for operations and maintenance. We can now take advantage of this model and add intelligence to each steel member through attributes to pass along information to the steel fabricator. This is part of the SMT process. So what is SMT? As mentioned before, SMT is Smart Model Transfer. This involves creating a three-dimensional model with intelligence and the ability to transfer material data to a fabricator. The data being transferred can be materials such as piles, embeds, pipe, or structural steel, to name a few. As I said before, in this presentation, we're going to focus on structural steel SMT. Fluor has a practice for SMT execution. This practice allows us to have the flexibility to meet the client's needs and make the best decisions for a project. We strive to use the model to transfer as much data as possible to a fabricator, depending on the fabricator's capabilities. In this simplified block diagram for the SMT workflow, the red arrows indicate manual transfer processes. The green arrows indicate digital transfer processes. The process starts with engineering and structural steel analysis. The engineering data is transferred to the three-dimensional model. The three-dimensional model is then transferred to the steel fabricator. Using the transferred data, the fabricator produces shop drawings, which are reviewed by the engineering and design team. The goal of the improved workflow is to eliminate as many manual transfer processes as possible to reduce the possibility of miscommunication and translation errors. Jonathan Litoff will now present some innovative ways we are converting manual data transfer processes for connection information to digital transfer processes.
Thank you, Eric, for providing an overview of Smart Model Transfer and the SMT workflow. The transfer of steel connection data from the engineer to the fabricator works in the same way as the transfer of all other structural steel data. When we're talking about transferring structural steel data, we're actually referring to each structural steel member's shape, material and grade, their start and end coordinates and their geometry, the steel member's rotation and orientation, and also their start and end frame connections, which provide information on how the steel connects within the structure. Each steel member, whether it is a column, beam, or brace that connects to another structural member, will have a connection code attribute assigned in the 3D model. These connection codes are all defined and illustrated on standard structural steel drawings, and an example of a standard beam to column connection found on these drawings is illustrated in the center of this slide. These connection codes provide the steel fabricator with critical information, such as the number and diameter of bolts used, connection plate dimensions, and weld sizes and locations. When Smart Model Transfer is utilized on a project, all of this data is stored in the model and can be extracted and sent directly to the fabricator in an electronic file, providing the fabricator with the information required for them to fully detail the steel connections, create a fabrication model, and also create shop drawings. The utilization of Smart Model Transfer can eliminate the need to produce many two-dimensional steel drawings, potentially reducing the number of engineering structural framing drawings by roughly 90%. However, with big data comes big responsibility, and it is imperative that the data is accessible, manageable, and able to be tracked. On a typical project that utilizes smart model transfer, the process begins with the engineer analyzing and designing the structural steel and steel connections. The engineer then provides this information to the design team to get the steel data incorporated into the model. A typical way that the engineer would communicate this information is by producing engineering sketches or drawings, which will then be incorporated into the model. Design would then add the steel from these sketches or drawings into the 3D model. And this is very rarely the final step in the process, since we all know design changes are very common and things can change as more information becomes available and as anticipated loading magnitude and locations may change. As more information becomes available, the engineers and designers will review the structural steel data in the model and make revisions as necessary. On projects utilizing SMT, where the structural data is stored in the model, a common way that this is handled is by generating auto sketches or two-dimensional drawings from the 3D model for the structural engineer to visualize the steel data during their review. The engineer can then mark up these sketches and drawings with their comments and send them back to the design team. And the design team would then reference the engineer's comments and update the model accordingly. This process is considered smart model transfer because the engineer and designers are working together to input, review, and revise this information in the 3D model, and then transmit this data electronically to the steel fabricator. However, since we're taking a data-centric approach, SMT affords us significant flexibility regarding how we actually get from point A to point B. This is only an example of some of the typical steps that may be taken when implementing smart model transfer as part of project execution. If we take a look to the right, we will see an illustration that summarizes the steps with red arrows. These red arrows indicate that there is still some manual transfer of data occurring. As we can see, there are still plenty of manual steps that can be improved in order to reduce the chances of miscommunication. Because smart model transfer is data-centric, the workflows are essentially future-proofed since they are very versatile and adaptable, and we can do useful things with this data. For example, we're able to export the data from our structural analysis software and import it directly into the 3D model. In the right situations, this is a significant improvement in reducing manual efforts. And not only is this a significantly more efficient use of the engineers and designers' time, but it also eliminates the chance of any unintentional errors or miscommunication occurring when updating the model per the engineer's design. Now, arguably, the largest part of this process is in the iterative review and revision steps. During these steps, design changes are common. Anticipated loading magnitudes and locations may change, which could result in the engineer needing to add or remove structural steel, revise steel shapes, and increase the capacity of some connections. One improvement that we've implemented is exporting the structural steel and connection data from the 3D model and importing it directly into the same structural analysis software that was used as part of the structural engineering calculations, as illustrated on this slide. Since the structural data is stored in the 3D model, we are able to access this data on demand and reformat the data to accomplish this as an alternative to producing two-dimensional drawings from the model for the engineer to review. In many situations, when the engineer is able to visualize the model's data right next to their calculation file, as shown in this illustration, the checking process becomes significantly easier. Additionally, this data-driven approach allows engineers to make comments or revisions directly in the structural analysis file and import the changes directly into the 3D model, which eliminates many manual steps improves checking accuracy and efficiency, and eliminates the possibility for miscommunications to occur. This also simplifies the process by reducing the number of steps, since the alternative would be for the engineer to review the two-dimensional drawings, provide their comments on the drawings, then the comments would be used to update the model manually, and then the engineer would review the updated model to confirm it matches their intended design and no miscommunications occurred. All of these steps are able to be consolidated into a single step, which results in not only increased accuracy, but also more transparency. And now I'm going to pass it over to Lorne Jensen, who will share his expertise on smart model transfer and review additional ways SMT is utilized by Fluor and the steel fabricator. Lorne, over to you.
Thank you, Jonathan, for providing an overview of automated connection call-out workflow between the analytical and the design model. I think this will make an excellent addition to the SMT suite of tools available to projects today. Looking back, the Cartesian coordinate system and descriptive geometry were invented back in the 1600s on the basis and are the basis of scale drafting today. The structural engineering drawing shown has been the proven method of communication in the industry, and drawings were either manually drafted by hand, 2D CAD, or 2D CAD extracted from a 3D model. Revision control was done manually by placing clouds around the modified items, and references to other drawings and details were used to show more information. Engineering notes saying typical 3 places or similar were required the steel fabricator to interpret where or the other locations are and what is considered similar. 2D drawings are prone to shortcuts being taken because of their flexibility to edit information directly on the drawing. A single project can have many structural engineering drawings, all which need to be managed by engineering and issued via document control. When drawings are extracted from 3D models, engineering could provide the 3D model to the fabricator as information only, since only the drawing is the stamp governing document. This would require the fabricator to remodel the structure using stamped engineering drawings, or start with an unofficial 3D model. This can take multiple days for the fabricator to rebuild the model before detailing can start. Structural engineering drawings still have their place in industry. However, they do require effort to create and can have quality issues when not maintained. Smart Model Transfer, referred to as SMT, is a Fluor CSA work process that transfers engineering information to the steel fabricator via open source data formats. SMT enables the steel fabricator to import the official stamped engineering models without the need of drawings. SMT uses SimSteel, or sometimes referred to as SIS2, which is ISO compliant and was specifically designed for the development of structural steel engineering data. SimSteel is an open source format that started in the early 1990s. Today it is endorsed by NIST, AISC, CISC, European, and all major software vendors for structural steel. Fluor's first SMT project was in 2014 and won the Tekla North American BIM Award for Modularized Industrial Project. This winning project was 500 tons of modular steel with no structural engineering drawings, no RFIs, and ahead of schedule. SMT builds a digital twin of the structure. All key information is within the SMT data. This opens the door to high-level machine learning and automation of routine engineering checks. SMT enables open accountability to prove that something has been done and how it has been done. Today, we will focus on transfer of structural steel, but other aspects of SMT, such as architectural, piles, and earthworks, are all part of the Smart Model Transfer family. Now we'll take a more in-depth review of the key steps of the SMT work process, which Fluor uses on projects today. This includes standard drawings, steel identification, connection callouts, data mining, and model reviews, along with issued for construction, steel fabricator, and the automated check. These steps can be adjusted based on the project connection strategy, whether it's done in-house, by fabricator, or third party. Also, if the project is modular, stick-built, or a variation of multiple fabricators being domestic or international. And lastly, if the steel is managed by Fluor or the client. Structural engineering standard drawings are a key to the SMT project setup and need to be fully incorporated into the model catalog. This ensures objects modeled automatically align to the standard by default. Items such as stairs, ladders, handrail, and flooring see large benefits in being well defined in the catalog. It is recommended the project steel table be limited to identify what is available from the fabricator, along with steel that may require a longer lead time. Material grades and coatings need to be assigned to the model to track items such as stainless steel, fireproofing, galvanizing, and painting requirements. Proper catalog configuration provides engineering the ability to pass significantly more information to the fabricator. This additional effort to configure the engineering catalog benefits engineering and all downstream consumers. Modeling tools such as Smart 3D has a live central catalog and model database shared across multiple global offices within a single project. File-based systems can require extra effort to maintain and ensure the model is always up to date bidirectionally. This may sound achievable and possible, but to sustain a file-based system throughout the entire life of a project, it does take effort to ensure the sync is always working. Data-centric execution gets the maximum potential of SMT. It allows CSA to see piping, mechanical, electrical, control systems, architectural, and HVAC design layouts in real time. SMT greatly expands the level of detail of each structural item modeled, as shown in the member types table. This provides engineering the ability to build a digital twin which clearly communicates to the fabricator the purpose of each modeled item. SMT also supports full revision control. After the first issuance of the structure, Fluor's internal SMT tools automatically report all revisions to the structure since it was last issued. This report is provided to the structural engineer for review and their approval to ensure these additions, modifications, and/or deletions are the ones they requested. Another significant benefit of SMT is the increased level of detail the model enables designers to learn more about structural design, fabrication, and construction. SMT has become an excellent learning tool to extend designer knowledge. Prior to the award of the contract to the fabricator, each fabricator needs to go to be pre-qualified for the SMT capabilities, and those findings should be included in the technical evaluation. SMT needs to be written into the fabrication contract as well to ensure the work process is adhered to. Connection assignments in the model can be connection callouts from standard drawings, project-specific details, or the fabricator's connection library. SMT is also flexible to have a combination of connection callouts or connection forces applied to the model, which allows the fabricator or third party to engineer the connections. Prior to the issue for construction, engineering will validate and approve connection assignments using Fluor internal tools. The SimSteel file is then stamped by engineering and issued to the fabricator with connection information embedded. For data mining, it is best if the structural engineering model can be accessed via live central repository. This ensures engineering has a single source of truth to review the data via web-based graphic dashboards, lookup tables, and filters to isolate structures. Dashboards automatically flag engineering validation issues to allow designers to do their own self-checks. A key part of SMT work process is the ability to automatically identify engineering modifications to the structures, which automates revision control. This greatly reduces cycle times to issue revisions to the fabricator. We have seen cycle times reduced up to 80% when compared to issuing traditional engineering drawings. When dealing with big data and data mining, it is important to note Smart 3D uses open source SQL database, which allows for a wide variety of software services, apps, and connectors to work together. This provides the ability to turn unrelated sources of data into coherent and visually interactive insights. For SMT internal squad checks, Smart Review or an equivalent is used. This model session file is submitted to document control for other engineering disciplines to review and sign off. Comments are added and tracked with internal tools to ensure they address the before and after snapshots with any additional information. The updates to the model are then reviewed for approval. The squad check model session has more information than traditional structural drawings, since they are multidisciplined and a static snapshot in time, which fully represents the structure at the time of the review. The usage of model sessions for squad check is a proven work process that's already well established for client reviews, and now is incorporated into the SMT work process. SMT has been used for all structure types across all Fluor business lines, including energy solutions, urban solutions, and mission solutions. To date, we have issued SMT structures as stick-built, modular land transport, modular ocean transport within greenfield or brownfield project sites. As mentioned earlier, each structure is packaged with one cover sheet drawing, which corresponds to one individual work breakdown structure, or WBS. The isometric cover sheet is mostly automatic, with only the general notes and reference tables being added manually. Additional engineering drawings can be added to the package for structural details that are too time-consuming to model or too complicated to communicate via the model. This could be a floor plate that has seal welding around it, but it's only partial. It's easier to draw a detail and create a drawing of that and pass it to the fabricator. SMT has reduced structural engineering drawings by 90%, which is a significant reduction in effort for designers in the preparation and management of drawings. This has also reduced the effort for document control, since they no longer need to push large number of drawings through the system. The SMT cover sheet contains all the information needed for the fabricator to import the engineering model and start detailing. This includes the SimSteel file, revision identification, and associated reference information. Once the SimSteel file is imported by the fabricator to the fabrication model, engineering and the fabrication models now become synced. Any future modifications loaded via the SimSteel file automatically update the fabrication model when imported. The Institute of Research in Construction stated in 2010 that most of the savings with transferring engineering model data to the fabricator would occur with steel detailing. We could see a reduction of detailing effort of 20 to 40%. And that engineering would provide, and that engineering model day would provide the steel fabricator the ability to get quicker quotations, faster detailing, earlier material orders, and reduce human errors. Today, in 2024, our experiences with SMT have shown these estimates are true. Here's an example from a project. We took a very large ocean transport module, or VLM, weighing approximately 3,500 tons, with dimensions of 70 meters long, 27 meters wide, and 25 meters high, which contained over 10,000 structural modeled objects. This single VLM was over 1.2 million rows of SMT data, which was fully imported into the fabrication model in less than 1 minute. Once imported, the steel detailing could proceed, since the SMT is the official engineering data we transfer to the fabricator. This is a significant savings in steel detailing effort for the fabricator. It eliminates the need to rebuild the fabrication model from scratch or verify a bootleg engineering model based on stamped engineering drawings. In the past, a structure of this size and complexity would require 100 to 120 engineering drawings to prepare for issuance, and then pass through document control, and then pass to the steel fabricator. In the slide, it shows an example of how the imported SMT engineering connection callout was automatically displayed on each end of the shop drawing beam. This is one simple method to ensure that data is being pushed through the system. There are various levels of automation skills among steel fabricators related to their steel detailing capabilities in SMT. Fabricators, which have invested in automation and work process refinement, have embraced the SMT work process and seen its benefits for themselves. It cannot be overstated that with big data, you need big solutions that are proven and scalable. Manual validation is extremely difficult, complicated, and not recommended with SMT. Data must be presented in a structured format to allow for proper controls and analysis. For SMT, we have developed work processes and automation tools which validate, manage revisions, and ensure data exchange protocols are being followed for every steel release. Once the fabrication models are ready for review, the steel fabricator provides engineering the first pass for commenting, which is prior to any erection and shop drawing creation. Fluor SMT tools can automatically find the differences between the engineering model and the fabrication model. This provides engineering the ability to check structural engineering members using machine learning. Here's an example of how Fluor SMT tools can do. On an engineering solutions project with 10,000 tons of steel, there is approximately 42,000 structural steel members. With each structural steel member having 2 connections, there is approximately 84,000 engineered connections assigned. Our SMT tools can verify multiple key points between the engineering model and the fabrication model, such as size, rotation, and points in material selection. This is over 290,000 automated checks on 10,000 tons of steel because of big data and machine learning. Any differences found are provided to the engineer for review. SMT creates a seamless workflow of data, which leads to overall reduced effort. The upper bar shows the effort for traditional drawing execution, while the bottom bar shows the corresponding SMT effort. Engineering effort has fundamentally not changed because of SMT, since the structure still needs to be engineered and the multidisciplinary aspects of face-to-face coordination, meetings, and engineering calculations still exist. For SMT, the design modeling effort has increased, since we are now spending more effort building an LOD 300 detailed design model with rich engineering data. The drafting effort for SMT has dramatically reduced, since the minimal structural engineering drawings are being prepared. However, as shown, SMT modeling and drafting effort combined is still less than the traditional drawing effort shown above. All downstream consumers and activities which handled the structural engineering drawings in the past have now greatly reduced in effort because the SMT reduced drawing count and automation. SMT has proven it can reduce effort, increase quality, and better manage change, along with preparing CSA for future and data-driven deliverables. The ability to have centralized, retrievable, and standardized data is what projects and the industry needs. Fluor has developed a global engineering data standard which supports all consumers of engineering data. This data standard ties to our core tools such as Smart 3D. Digital transformation enables us to integrate and organize data from feed, detailed engineering, procurement, fabrication, and construction. Fluor's data-centric execution strategy is based on data standardization, data collection, data quality, and data management. CSA uses big data to openly share engineering information to other disciplines, management, and subcontractors. The future intent is to develop a concept of a smart project in which engineering shares most of its information via data and not Excel files or manually marked up documents. Today, with SMT, there is no need for other disciplines or management to wait for drawings. The SMT workflow allows for data to be accessed via the model or live dashboards. Data can be sorted as either working or approved for consumers to develop their own insights. When sharing data, there are 3 key components which must be followed. First is the network. There must be a digital backbone solution. The data can be used by various applications. Next is connectivity. This enables engineering disciplines to interact directly with the project and have access to live data. And last, open data. For smart model transfer to reach its maximum potential, data created and shared must be open source. It cannot be locked to a single proprietary format or to specific software vendor. Here's some of the highlights we have achieved with smart model transfer at Fluor. First, with steel. We can automatically compare engineering model data to fabrication model data and find all the differences. Second, revision control is automatic by reviewing the engineering for issuance of each structure. And to date, we've issued 400,000 tons of steel across multiple business lines on 30 plus projects worldwide to more than 15 different steel fabricators globally. Next is architectural. While using Smart 3D on energy solution projects, architectural model data was exported and stamped by engineering, which was provided to subcontractors with no drawings. Local permitting was required, but of much less detail than full architectural drawing packages. The architectural model was a full digital twin with weight, fabrication requirement, revision control of each modeled object. The weight information was needed to calculate the total weight and center of gravity of cladded modules. Another area for smart model transfer has been piles. Only the model was used as a deliverable, which included revision control of each pile. The model pile includes all the required information for procurement, fabrication, and installation. This method allows for the pile data to be loaded directly to the survey total station to stake pile locations. To date, we've issued, purchased, and installed over 5,000 piles via data, along with the elimination of pile schedule drawings. And lastly, civil. For civil, we have earthworks. Rough grading models can be exchanged today using industry standard formats that can be loaded directly into survey total stations and machine-controlled excavation equipment. Not widely used at this time due to contractor selection, but this technology reduces field layout times, eliminates over-excavation, eliminates human error of data entry, can verify grade and angles, and lastly, monitor progress of earthwork at the construction site in real time. Successful data management can provide more accurate and precise information, which can reduce engineering cycle times, reduce claims from construction, reduce RFIs from fabricators, reduce vendor schedule, and reduce human errors. All of these reductions contribute to increased safety for the project. Fabricators have indicated they have seen benefits of SMT since they can talk over the model and resolve issues more effectively because of the level of detail provided in engineering model data. Fabricators have stated there is a reduction of cycle times up to 2 weeks because of elimination of early erection and shop drawings for review, and instead utilizing the fabrication model. A significant reduction in drafting RFIs due to the clarity of SMT model data, and that SMT is a better way of communicating connection loads and design information to the fabricator. Revisions can be accessed quickly and efficiently, and fabricators can quickly quantify specialty items such as embedded plates, Teflon slide plates, equipment bolting by allowing us to access the materials directly from the model. All consumers benefit from SMT data since they are provided the data they need in the format they can consume. As a last note, the generation just beginning to enter the workforce has grown up with the digital devices and may have never known a time without high-speed internet. A world of information, entertainment, and digital content has always been at their fingertips. A data solution like Fluor's Smart Model Transfer is a natural transition to the up-and-coming engineering workforce. Thank you. I'll return the presentation back to Dave for Q&A.
All right. Well, thank you very much, Lorne. That was great and a very, very interesting topic. Let's take a few moments now to address some questions that we've received in from the audience during the presentation. And for those who are dialed in, it's a reminder, please make use of the Q&A tab to certainly ask any further questions, which should be addressed to all panelists. So let's get started here with some of the questions that have come in from our audience. And this first one here, I'm going to ask Jonathan to help us out with. And the question is this, Jonathan. Is the use of SMT limited to certain software packages? Could you comment to that?
Yes, thank you for that question. The use of SMT isn't limited in any capacity by the software used in the engineering calculations. I could see the use of SMT potentially being limited by the software that's used to manage the 3D model, but assuming that the 3D modeling software allows for assigning attributes and exporting data, then I think it should be compatible. I think I'd like to pass on this question to my colleague Lorne, who knows a lot more about 3D modeling software. Lorne, do you have anything else you want to add?
Yeah, sure do, Jonathan. Thanks. It's a good question as well, and something that I know when we started with SMT, we were trying to find solutions. For smaller projects, I would say that you would have more ability to use other software tools, but like Jonathan said, have to have a modeling tool that has data-rich capabilities that you can assign attributes, and also pass those attributes to the steel fabricator. That is fundamental in making this happen. However, when you get to larger projects, say 50,000 or 80,000 tons of steel, file-based systems could be complicated and difficult. So if there's ways you can get your file-based system into a data-centric database to analyze the data and do big data solutions and data machine learning, that would be recommended. But then again, there is software tools out there that are already data-centric and already have this capability built into them. But it's all based on investment and the right tool for the right job.
All right, that's great. Thank you very much, Jonathan and Lorne. Lorne, this next question I'm going to ask of you, and I think you've already alluded to it, and I'll ask you if you've got any more to add, but this is the question from an audience member. Is the use of SMT limited to projects of a certain size?
Yeah, we did slightly touch on it, but I'll address it in more detail. Once you have the work process set up, I think we've seen projects down to 100 tons of steel successful with SMT, but to spend the investment and the time to define a work process, you may not have the time to do that within that project schedule or availability. So it kind of has to be something that you have to develop the work process offline, and then you can adapt it to projects. But we have done projects from 100 tons up to 120,000 tons of steel. So I don't think it's limited. It's a natural progression of just sending information to the fabricator.
Okay, excellent. I'm going to stick with you, Lorne, for this next question here, and I think it's very relevant to the conversation we've had today. And it is this: does the use of SMT save effort hours on the job?
When we look from say initial engineering all the way to construction, I definitely think it does save. When you look at just engineering itself, I don't think the engineers see much saving, because as I mentioned in the presentation, the engineers still need to do their work, do their calculations, do their analysis, talk to the disciplines. So the engineering of the structure is still a very specific activity, which we don't interrupt. However, once it gets to the designer and to the fabricator, when you get into revision control and passing of data for automated updates, there is an effort reduction there, which turns into schedule reduction. But also there's the ability to send clean, clear data that's always with little human error to it, or if no human error. So you have potential savings of things you would not have ran into in RFIs and delays because of sending drawings through PDDM or document control, right, or other handling issues. So I think we see it as savings, but it's a kind of intangible because it's things you would not have happen on the project if you use drawings, right?
Okay, great. And I think you also answered another question that we get in from the audience in regards to schedule there as well. So thanks for addressing that in that response. Okay, Jonathan, I'm going to come back to you here. And the question is this: what type of drawings will remain required even if using SMT?
Thank you for that question. Using Smart Model Transfer, it won't eliminate the requirement to have standard steel connection drawings and other sets of standard structural drawings, since these drawings provide a lot of information to the fabricator and they need that information to do their detailing. So it won't affect any of the standard drawings. Additionally, drawings that may be required for instances where a non-standard or unique steel connection is required, where it's not shown on the standard. So those kinds of drawings would still be required.
Okay, excellent. Thank you.
And I can add to that one other area, David, that I'm aware of is in zones where there's high seismic, local permitting does require sometimes a structural engineering drawing to be submitted for permitting for high seismic zones. So in those conditions, we do need to meet the local jurisdiction, their requirements as well.
Okay, excellent. I'm going to go back to you here, Lorne, and it is a question that relates to our relationships with fabricators. And the question is this: have you seen a reduction in fabricator costs using SMT?
We have seen our procurement and contracts people have confirmed there's been a reduction in claims and a significant reduction in RFIs. So I think the initial, say the agreed contractual costs probably is not less at the start of the project. However, any add-ons or any runovers, we have seen reductions related to RFIs and related to claims. I think there's some efficiencies, say on the steel detailing side, some savings for the steel fabricator. However, many times steel fabricators consider detailing to be just part of the internal cost of the contract, and they don't really put a price on it. But there is efficiencies that we gain, which turns into schedule and cost savings.
All right, I'm going to stick with you, Lorne, because there's another question that's come in here that relates to fabricators, and it relates to what you just shared with us. And here's the question: is Fluor finding that the fabricators out there are able to align with this improved workflow? Or are you seeing maybe any limitations on the fabricators' side that, might require them to still require like further internal development or investments that relate to this work process? Thoughts on that?
Yeah, to date, we worked with, I think, approximately 15 fabricators globally. Some of them, it was their first SMT project. They never worked on it before. We were able to sit with them and walk them through the process, and they were successful through the project. There is some basic fundamentals of they need to have their software, their detailing software up to date. They need to have the ability to, if their internal work processes don't allow for, say, how they handle drawings, or if they are usually subcontracting out their detailing, that those subcontracted detailing shops need to also be aware of the work process. But so far, every fabricator we worked with that's been selected, we've been able to meet with them and go through the work process, and they're able to complete the task. It is a software requirement, though, of some basic software technology they need to have in place.
Okay, wonderful. Thank you. Eric, I'm going to come over to you on this one because I know it speaks directly to your background and your experience. And here's the question: can you use SMT in a project with seismic detailing for AISC 341? Thoughts on that?
Yes, thanks for the question. So detailing for AISC 341 is for higher seismic risk areas. In those areas, the simple answer is yes, it can be used. It lends itself to the engineering firm fully detailing their structural steel connections as opposed to delegating the connection design. Because, Using AISC 341, the steel members, sizes, and the connections are interrelated. This lends itself to the process that Jonathan presented earlier in this presentation, where you have engineering connections that are transferred to the fabricator through the model.
Okay, excellent, Eric. Thanks very much. And I think just looking at the clock here, we have time for maybe one more question. And I'll open this to either Lorne, Jonathan, or Eric to chime in on. And this is a question from our audience member here. When transferring data between structural analysis, a structural analysis model, and a 3D design model, is there an ability to have an automated comparison tool to identify differences or changes between the two? Any thoughts on that, folks?
Yes, I can take the initial response to that. In short, the answer is yes, and that is the tool that we are using at Fluor does have that automated check, and it's already built into the tool, and it does the comparison check between any revisions being made before it gets updated into the model.
Okay,
and
great.
I'll just add to that what Jonathan mentioned, and the reason we're able to do this in Fluor is because the tools we use are open source tools. So people like Jonathan and other people that are working on SMT can build tools to do this work for checking, because we work with open source data, right? So that is a key component.
All right. Well, that's great. Thanks to both of you for that one. All right. Well, we're getting close to the top of the hour here. It looks like that's all the time we have for questions today. I'd like to thank Bradley. I'd like to thank Eric, Jonathan, and Lorne for what I'd call an informative webinar, and certainly the time that you've spent with us both here today and in preparation leading up to today's event. Also, thank you to our audience for attending today. It certainly has been a pleasure being your moderator. So please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com, following our social media channels, or using hashtag Innovation Builders. And if you'd like us to send you email notifications on future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention, and again, thank you for dialing in today. We will send out a compiled list of the questions and the answers shortly, along with a notification that the webinar recording is available for replay on fluor.com. If you have any questions or if you require any additional information, please email innovation.builders@fluor.com, and someone from our team will certainly get back to you. And finally, from all of us at the Innovation Builders team, have a wonderful day, and thank you very much.